So this is Donna Nelson. We're going to continue with our discussion of Chapter 16. Now we're going to look at orbital control reactions and the molecular orbital theory that explains that. So, remember I mentioned in the previous discussion that molecular orbital theory, section 3, is going to be moved down into the discussion with section 6 and 7. So that's this section. And so we're going to start out now with the molecular orbital theory, because the molecular orbital theory fits and is required by these discussions of pericyclic reactions rather than these charge-controlled reactions that go through carbocations. So let's look at this. So when you bring two atoms into close proximity so that they can interact, and here we're looking at the p orbitals on those two atoms, and as they get closer and they start to interact, the electrons in those two p orbitals can interact constructively or destructively. And so if they interact constructively, they will form a bond. This is a bonding orbital. The destructive interaction would be higher in energy, and that would correspond to this anti-bonding orbital up here. And so you can see in the bonding MO, the p orbitals have overlapped and indeed form this pi bond. Up here, they are interacting destructively, and you can see that they have formed an anti-bonding MO, and you can see this node in between. In the bonding molecular orbital, notice there is no node. Up here, there is a node, so that means there is no bonding interaction. And so that's why this is called anti-bonding. And I emphasize here that these are indeed molecular orbitals. These are the drawings of the molecular orbitals. You're going to see drawings of atomic orbitals and drawings of molecular orbitals. And the drawings of the atomic orbitals are given as an approximation for the molecular orbitals. And so you'll have to not get those confused. But these are the molecular orbitals, bonding and anti-bonding. The two electrons go into the bonding MO, and the anti-bonding orbital is left unoccupied. So those were the orbitals for ethylene, just one pi bond. And so now we're going to look at the orbitals for butadiene. So that's a molecule that has two pi bonds. And so you can see here, these are the molecular orbitals, and these are the atomic orbitals. So over here you can see that you can clearly recognize the molecular orbitals of butadiene, because here the orbital is spread out over all four atoms. So here you can see in the atomic orbitals, the p orbitals are still very distinct for those four carbon atoms. So these four p orbitals can overlap to form molecular orbitals. These are the atomic orbitals. These are the atomic orbitals. These are the drawings of the molecular orbitals. You can see the lowest energy. This shows the energy. You can see the lowest energy molecular orbital has no nodes. So in other words, there's overlap across all four atoms involving all four of those atomic orbitals. And you can see it here. You can see the phase, or the signs of the two lobes. Up here we're using a blue lobe and a red lobe, so you can see there's overlap across all of the blue lobes and overlap across all of the red lobes. Now, when we have a node in between, you can see that there is no overlap between the blue lobe and the red lobe, blue and red. There's only overlap across the lobes that have the same sign or the same color. And so here you can see there's overlap, here there's overlap, here there is no overlap. So this is called a node. There is no interaction here. Here there's a constructive interaction across all four of the atoms. And you can see this, so this you can think of as an atomic orbital representation of the molecular orbital. This molecular orbital is much closer to what actually exists. And so that orbital is just a region of space in which the electron, the pi electron, might be found. Here you can see the bonding interaction between the two carbons. Here there's a bonding interaction, and here there's a node. So the node is the point in space in which there is zero probability of finding an electron. And so you're going to find the electrons only over here and over here in the second molecular orbital. Notice there are 4 molecular orbitals, 4 atomic orbitals also. And so if you have 2 pi bonds, that means you're going to have 4 carbon atoms that are contributing. Each contributes 1 p orbital. And so that's why you have a p orbital here, a p orbital here, a p orbital here, a p orbital here that can interact in the pi bond. And that's why you have 4 p orbitals here. So if you have 4 p orbitals going in to form the molecular orbitals, you're going to have 4 molecular orbitals formed. 4 p orbitals, 4 molecular orbitals. And here are those molecular orbitals. You can see as you go up in energy, you will increase the number of nodes. So the most stable molecular orbital has 0 nodes. The one with 1 node is increased in energy. The one with 2 nodes is a little bit higher. The molecular orbital with 3 nodes is the highest. So notice this one, the highest molecular orbital has no bonding interactions. It's only anti-bonding interactions, red, blue, red, blue. And over here, you can see the same thing, red, blue, red, blue. These are the atomic orbital representations of the molecular orbitals. So these represent the same things, but just differently. These are the atomic orbital representations. These are molecular orbitals. And notice again, 0 nodes, 1 node, 2 nodes, 3 nodes. So you can have overlap between the orbitals that are of the same sign. And so that's here, or all across here, up here, and here there's no constructive interaction, no overlap, no constructive overlap. So there's nodes between each 2 consecutive p orbitals. So here you can see you would expect there to be bonding interactions between C1, C2, C2, C3, C3, C4 in the lowest molecular orbital. In the next highest energy molecular orbital, you're going to expect bonding interactions between C1, C2, and C3, C4, but none between C2 and C3. And so These are the two that are occupied. There's 4 pi electrons in this molecule. They will go into the lowest energy molecular orbitals. So 2 go into psi 1, 2 go into psi 2, none of them go into psi 3, and none go into psi 4. So these orbitals are left unoccupied because they're higher in energy. So where will you be likely to find electron density? Since these 2 orbitals are the ones that are populated, you're going to find electron density between C1 and C2, C3 and C4. You would expect those to be equal because of the symmetry of the molecule, but you'll expect to find less between C2 and C3, because there's a node between C2 and C3 in psi 2. In this molecular orbital is the node, and so you have no bonding interaction to that contributing to the bonding of the molecule between C2 and C3 in psi 2. So that explains some of the reactions that we see later on. So now, the 4 pi orbitals in butadiene occupy the lowest energy molecular orbitals, and here only the lowest energy molecular orbitals, psi 1 and psi 2, are shown here. Once again, these are atomic orbital representations, so these are just a little bit larger and easier to see. And you can see there's interaction across all 4 of the p orbitals. Here there's interaction between C1 and C2, C3 and C4, but then between C2 and C3 in this particular molecular orbital. Both of these molecular orbitals will contribute to the actual molecule, just like both of these molecular orbitals will contribute to the actual electron density in the molecule. So these are atomic orbitals, molecular orbitals. Here you can see the node again. Down here in psi 1, there is no node. Since the actual electron density, etc., will be a contribution of both of these, psi 1 and psi 2, which are occupied, then you're going to have some electron density between C2 and C3 contributed from psi 1, but you will have none contributed from psi 2. Now let's look at 135 hexatriene. Here is 135 hexatriene. 1, 2, 3, 4, 5, 6 sp2 hybridized carbons, 6 p orbitals. Here they are. So these are atomic orbitals. These are the molecular orbitals. These are the atomic orbitals. You can see the lowest energy orbitals are at the bottom. The highest are at the top. The lowest ones have no nodes. The highest one has 5 nodes, no bonding interactions. This is the highest energy molecular orbital. This is the AO model of that molecular orbital. You have 6 pi electrons, 1, 2, 3, 4, 5, 6. So these 3 molecular orbitals, and these are the atomic orbital representations or atomic orbital approximations for the molecular orbitals. These molecular orbitals, these 3 that are the lowest in energy, will each be occupied with 2 electrons. And so you can see those 2 electrons over here, 2 electrons, 2 electrons, 2 electrons. The psi 1 has no nodes. Psi 2, which is next highest in energy, has 1 node. Psi 3, which is next highest in energy, has 2 nodes. Now, we very often just look at the molecular orbitals that are occupied, because the molecular orbitals that are not occupied usually do not participate significantly in the reactions. However, in orbital controlled reactions, the very lowest energy unoccupied orbital, here that would be this one, the one just above the highest energy molecular orbital that is occupied. So this one, this unoccupied orbital, can be important. The other two will not. So this one you might need to keep track of in some reactions, but usually because it gets very complicated in the larger molecules, we won't use the larger molecules as examples very often. We'll usually use the smaller molecules where the orbitals are easier to figure out and to visualize. But anyway, the ones that are important are the occupied ones. In particular, the ones that are very important in the orbital controlled reactions are, there's two. This highest energy one of the occupied orbitals and the lowest energy of the unoccupied orbitals. So in this case, it would be psi 3 and psi 4. Here, this one is occupied. This is the highest energy of the occupied orbitals. This one is unoccupied. This is the lowest energy of the unoccupied orbitals. So these two could be important in reactions of 1,3,5-hexatriene. And so we would just have to look at the reaction that we're considering in order to determine which of these is important. It could be psi 3 or it could be psi 4. We would need to know what it's reacting with in order to know which one of those is important. So, as I was mentioning, here is another demonstration of it. This is the ground state. Here you can see the highest occupied molecular orbital, HOMO, highest occupied. This is the occupied, these are the occupied molecular orbitals. This is the highest energy occupied molecular orbital. These are the unoccupied molecular orbitals. This is the lowest energy unoccupied molecular orbital. These are often abbreviated HOMO and LUMO. So, but that corresponds to highest occupied molecular orbital, lowest unoccupied molecular orbital, LUMO. Okay, and these orbitals, HOMO and LUMO, are considered the frontier molecular orbitals. These are the ones that will be interacting in an orbital controlled reaction. And so these orbital controlled reactions can occur either thermally or photochemically. If they occur thermally, you're going to be using the ground state molecular orbitals. If they occur photochemically, then you're going to be using at least one excited state. And when that happens, in the excited state, what happens is one of the electrons in the HOMO gets promoted to the LUMO. So the ground state molecule, one of the electrons gets promoted up to the LUMO, from the HOMO to the LUMO. When that happens, this molecule is no longer unoccupied. It becomes the HOMO, and the one above it becomes the LUMO. And so you have, one of the first things that you have to determine is, do you have a thermal reaction in which you would use ground state orbitals, or do you have a photochemical reaction where you would use the excited state orbitals? And this is with the orbital controlled reactions. And so we're going to look at some of those in a minute. So the pericyclic reactions, we're only going to consider 3 of the 4 types. There's a 4th type, which there are many fewer examples, but it is there. and we're not going to cover it because it's a little more obscure. But the three major types are the cycloaddition. You can see that the electrons are flowing in a ring, and so they flow in a ring, and so this is a 4+2 reaction. So you have butadiene plus ethylene gives you cyclohexene. Then there's the electrocyclic reaction, in which, once again, the electrons are flowing in a circle, and you can see that you have, once again, you have 3 pi bonds. Up here you had 3 pi bonds. Down here you have 3 pi bonds. And so in this reaction, it's just one molecule. Up here you had 2 molecules coming together in a cycloaddition. Here you have one molecule, and what's happening, this one linear molecule is becoming a cyclic molecule. So this is called an electrocyclic reaction. The electrons are moving in a circle to give you a cyclic product. And then there's the sigmatropic rearrangement. Once again, you have 6 electrons involved, but here 4 of them are in 2 pi bonds. The 2 remaining electrons are in a sigma bond. And so here the electrons are flowing again in a circle, and this amounts to, the sigmatropic rearrangement amounts to a sigma bond migrating down 2 pi systems. Okay, see, this is a pi system over here, this is a pi system over here, and now the pi systems have rearranged. Now you have the pi system here and the pi system here, and this sigma bond has migrated from one end of the molecule to the other. Pericyclic reactions, regardless of which type they are, have 4 characteristic features. The reaction mechanism is concerted. It's never stepwise. It proceeds without any intermediates, so there's no charged intermediates involved. There's no charge control. The mechanism involves a ring of electrons moving around a closed loop. The transition state is cyclic, and actually you can think of it as aromatic. And so that's what makes these reactions occur so easily, is that they're actually going through an aromatic transition state. The polarity of the solvent has no effect because there's no charge being developed during the reaction. So the transition state has no charge, and so there's no solvent stabilization possible. I don't know that it would do you a lot of good to memorize this table. This table is just interesting in that you can see the change in the number. You might just want to look at it and look at the reactions on this previous slide, and ensure yourself in your own mind that you do see. Here you have 2 pi bonds that are being converted to 2 sigma bonds. Here you have a pi bond being converted to a sigma bond. And here you have no change. You have 2 pi bonds and a sigma bond, 2 pi bonds and a sigma bond. You might just want to look at that and see the 2 pi bonds are being converted to 2 sigma bonds. 1 pi bond is being converted to 1 sigma bond, and in the sigmatropic reaction, there's no change. So you might just want to go through that and ensure to yourself that you understand this, but I don't think it would help you any to actually memorize this table. It would help much more to just understand what's happening. The Diels-Alder reaction is a very useful reaction. Here you see it's a 4+2 So you can see that there's these two pi bonds are being lost. This pi bond is being lost. You have 1, 2 sigma bonds being formed, and this pi bond is over here and is a new pi bond. The same thing here, you can see it, this pi bond is the new pi bond that is being formed. And here are the two new sigma bonds. It doesn't matter if you draw the arrows clockwise or counterclockwise, they mean the same thing. This is often called a 4+2 cycloaddition. So now you can see on a potential energy diagram, these two come in close proximity so that the pi systems start to interact. When the pi systems get close enough that they can interact, this end of the pi system and that end of the pi system come in close proximity to this pi system, the two ends of this pi system, and you can see the electrons just flow in a circle. Think like the electrons flowing in an aromatic ring. You know, they're flowing in a circle here. In an aromatic ring, benzene, you have 6 pi electrons. And look at this, 2, 4, 6 electrons flowing in a circle, just like benzene. And so this reaction occurs, and here is the product. So that's one of the reasons that the Diels-Alder reaction can occur at low or moderate temperatures, is because it's going through a very favorable transition state, favorable electronically. So you can have the Diels-Alder reaction going forward, and you can have the retro Diels-Alder reaction taking place at higher temperature. You can see that the entropy of the reaction here, in the retro reaction, you're going from 1 molecule to 2 molecules, and so with entropy will favor the retro reaction, but thermodynamically, the forward Diels-Alder reaction will be favored because you're losing 2 pi bonds and gaining 2 sigma bonds. And sigma bonds are stronger. They give more stabilization to the molecule. So the strength of a pi bond, I'm not talking about a double bond, I'm talking about just a pi bond. The strength of the pi bond is less. So you're losing 2 pi bonds and gaining 2 sigma bonds. And so thermodynamically, the forward direction is favored. Entropically, the retro is favored. And so that means that the determining factor here comes down to what's the temperature. And like we said earlier, at lower temperature, this term will not be very important. And so the forward direction will predominate, the forward reaction. However, at a very high temperature, this entropy term will predominate. And so that means that the retro reaction will predominate. Okay. So in the Diels-Alder reactions, these are called the diene and the dienophile. It's very helpful if the dienophile bears an electron withdrawing group. It makes it more facile. It makes the reaction more facile. And it makes the orbitals actually line up a little bit better because the orbital of the dienophile is shifted a little to overlap better with the orbitals of the diene. And so it doesn't need to possess an electron withdrawing group, but it can occur much more readily if it does. It just facilitates the reaction. So here you can see an electron withdrawing group. Here you have an electron withdrawing group. Let's go back and look at something else for just a minute. Okay, so here, notice there's no electron withdrawing group. 200 degrees centigrade are required and only 20% of the product. Now, you have an electron withdrawing group and you have 100% yield. So these are all electron withdrawing groups. If you'll look at each one of these, this is a carbon bonded to an electronegative atom, carbon, electronegative atom, carbon, electronegative atom. Here, this is carbon bonded to an electronegative atom. In each case, the carbon here is going to bear a significant partial positive charge that makes these electron withdrawing groups. And so that would facilitate the Diels-Alder reaction. Regarding the stereospecificity of the reaction, so if you have a cis reactant, you will wind up with a cis product. If you have a trans reactant, you wind up with a trans product. You can also have an alkyne function as the dienophile. Notice in both cases, you've got both carbons, you've got two electron withdrawing groups. Remember that the diene can exist either in, this is called the S-cis. The S stands for single bond. So here, this diene, both of the double bonds are on the same side of the single bond. Here, the two double bonds are on opposite sides of the single bond. So S-trans means single bond trans. And so when you have this configuration, it's not going to be able to overlap with the dienophile. So notice here, you have the two double bonds on opposite sides of the single bond here. So these two ends of the diene cannot come close to the two ends of the dienophile. And so you're not going to get good overlap. And this is an orbital controlled reaction. And so you must have good overlap between the ends of one pi system and the ends of the other pi system, or else the reaction will not take place. Here, and notice this is involved in a ring structure so that it is held in the S-trans configuration. Now we have the two double bonds involved in a ring structure where they are held in the S-cis configuration. And so there's no free rotation about this single bond. And so they are held in the conformation that is necessary for the reaction to take place. And so it is very easy for these to react now with the dienophile. And that does indeed take place. And notice that this was a trans double bond, and now you have a trans relationship between the two substituents. One X is on one side of the ring in the product, the other X is on the other side of the ring in the product. So this is indeed stereospecific, as mentioned earlier. the cyclopentadiene can react with itself. It will react with one of the double bonds, and that's what's happened here. Notice here, this was the cyclopentadiene. This is the 5-membered ring that was this cyclopentadiene. This 5-membered ring over here was this cyclopentadiene. And so this end of the pi system and that end of the pi system have reacted with these two ends of the pi system here. This double bond is just a spectator. You ignore this double bond. Nothing happens with it. Only one of the double bonds is active. So this spectator just goes through the reaction intact. So the two new bonds that are formed are here and here. Okay, so both of the two new double bonds are right here. You can see the 5-membered ring over here, the 5-membered ring over there. And the interesting thing about this, notice that you could have had these two react in a manner such that this double bond was up instead of down. Let's go back to that. See, here it could have gone up the way this X went up. One X went down, one X went up. Over here, this ring could have gone up. Instead, it went down. If you look over here at what happens, this moiety will react either with this 1-carbon bridge or this 2-carbon bridge. Now, it turns out that the 1-carbon bridge is much less sterically hindered. And so one might think that this new ring would point up next to this less sterically hindered bridge. But actually, it points down towards this more sterically hindered bridge. And so the question then would be, why are you getting the more sterically hindered molecule? And the reason is that because there is an interaction between this pi system and that pi system. This spectator pi system and this incipient pi bond interact favorably to pull this moiety down close to it. So, in line with what I was just saying, here is another example. You can have the two substituents either pointing down towards the 2-carbon bridge, which is larger, or you can have them pointing up towards the 1-carbon bridge, which is smaller, less steric hindrance. So this product will have less steric hindrance in the product and also in the transition state leading to the product. This product will have more steric hindrance in the product and also more steric hindrance in the transition state leading to the product. So the interaction that is happening to favor this more sterically hindered product is overriding. The electronic effects are overriding the steric effects here. By the way, the isomer that has the two substituents closer to the larger bridge, the more sterically hindered product, is called endo, because both of these substituents are pointing or in closer proximity to the larger bridge, so it's called endo. The other stereoisomer, where the two groups are pointing up in closer proximity to the smaller bridge, is called exo. This is the minor product, this is the major product, That's not what you would expect just due to steric effects, but these electronic effects are overriding the steric effects. The electronic effects they happen when you have a pi system. Notice this will have a carbon double bond oxygen, carbon double bond oxygen. So there's pi systems on these substituents or in these substituents, and they will interact with the pi system back here. This incipient carbon-carbon double bond will interact with this pi system in a way favorably, so that it favors this endo product. And so in the next lecture, we will go on to other pericyclic reactions.